structure. Here we know that two hydrogen atoms in the water molecule are completely identical and we cannot distinguish them. Just to label them, we have mentioned that the left hand side hydrogen is H1 and the right hand side hydrogen is H2. But if we rotate the molecule through the axis by 180 degree, so we cannot distinguish the change happened to that molecule. So here we cannot distinguish and say that we have performed a symmetry operation. So that is called symmetry operation, and the symmetry operation is called rotation by 180 degree. Thus, we can define the symmetry operation as well. Define non-translational real movement which when performed on a body leaves the body in a position that is indistinguishable from its original position. That means if we perform any operation to any molecule, so after the operation, if the molecule will be indistinguishable from its original position, then that operation is called symmetry operation. So here the line or axis around which the molecule was rotated is called axis of rotation. That is one symmetry element. So the axis we used was the axis passing through the oxygen atom in the molecular plane. A symmetry element could be and similarly a symmetry element could be a point that may be so different types of here we have discussed that the symmetry element, so that is the symmetry axis, and similarly the other symmetry elements that may be a point, that may be a line, or may be a plane with respect to which the symmetry operation is performed. It is important to know that a symmetry element is not physical entity but an imaginary point, line or plane. So the symmetry element consists of all the points that stay in the same place when the symmetry operation is performed. For example, in a rotation operation described above, the line of points that stay in the same place constitute one symmetry axis. So here take our discussion further and perform another rotation by 180 degree. So this is the original position of the water molecule. In the first step, we have performed the rotation by 180 degree about the internuclear axis. So here this one is the symmetry axis. In the first step, we have performed rotation about 180 degree, so that you will get this type of indistinguishable structure than that of the original structure. And in the second step, again we will rotate the molecule by 180 degree, then the initial structure will be arrived. So we find that the water molecule has come back to its original state. So this is the original state, this one is the original state, and this one is the state appeared after rotation by 180 degree, and practically you cannot distinguish the original and final step of the water molecule about that rotation 180 degree. So that is called symmetry operation. In general, the successive application of the symmetry operation ultimately brings the body back into original state. And again, you may ask, what is the difference between the result of the first and second rotation? There is a very little difference, and after the first rotation, the water molecule was an equivalent configuration, whereas after the second rotation, we get identical configuration. So that means after the first rotation, we will get equivalent configuration, and after the second rotation, we will get identical configuration. So now, after this example, we will discuss what are the different molecular symmetry elements exist. So the first one is, so these are the list of molecular symmetry operations and the corresponding symmetry elements. So serial number 1, that is the symmetry operation that is rotation by an angle 360 degree divided by n around the axis, and n must be one integer. So that may be n must be 1, 2, 3, whatever may be. So if the molecule, by if identical equivalent structure will come after the rotation of an angle 360 divided by n, where n is an integer, then the symmetry element exists in the molecule, that is called n-fold axis of symmetry or proper axis of symmetry, that is called Cn. And similarly other molecular symmetry operations, the number 2, that is reflection in a plane processing through the molecule, that is called plane of symmetry. Suppose this is the water molecule. Again, we will consider the same water molecule. Now, if we will consider one imaginary plane passing through the water molecule like this. So, if we will consider this is the imaginary plane passing through the water molecule, and if the plane will divide the molecule into two equal halves, into two identical parts, then that operation is called reflection in the plane passing through the molecule. That means here, after if we divide the molecule through this plane, then the left hand part, then the left hand side is the mirror image of the right hand side. So that's why that is called reflection in a plane passing through the molecule. So that is called plane of symmetry sigma. First one, the first we have discussed, that is called axis of symmetry Cn, axis of symmetry Cn, and the second one, that is called plane of symmetry sigma. And then coming to the third one is rotation about an axis by an angle 360 degree divided by n, followed by so here, the third one is rotation by an axis by an angle 360 degree divided by n, followed by a reflection in a plane perpendicular to the axis of rotation. So that is called axis of improper rotation or alternative axis of symmetry, or that is designated as Sn. So the first one designated as Cn, then the second one, that is called plane of symmetry, that is sigma, and the third one, that is called axis of improper rotation, that is designated as Sn. And the fourth one, that is inversion of all the atoms through a point of the molecule that is called center of inversion. So here the center of symmetry, so that is known as center of symmetry. So all these different symmetry elements we will discuss in details. So that is called center of symmetry I. And the fifth one is doing nothing to the object, that is called identity element E. So here we will discuss the first one, that is called proper axis of symmetry CN. So the proper axis of symmetry is a line about which a molecule is to be rotated through an angle 360 divided by n to obtain an equivalent configuration. Then it is called n-fold axis of symmetry and it is denoted as Cn. And the symbol C here stands for the circular rotation around the axis, and the subscript n here called the the order of the axis, and it is defined as order of axis equals to n, which is equals to 360 divided by minimum angle of rotation for obtaining equivalent configuration. Again, the order of axis n equals 360 divided by minimum angle of rotation for about equivalent configuration. Now, for the water molecule, we have discussed in order to get equivalent configuration by so rotating the molecule, definitely you have to rotate the molecule by 180 degree to get one equivalent configuration. So a rotation of 180 degree, that means which is equal to 360 divided by 2 around an axis passing through the oxygen atom and lying in the plane of the molecule results an equivalent configuration. So here n equals to 360 divided by 180, that is called 2. So here for water molecule, the axis of rotation in the water molecule has an order of 2, and that's why that is called two-fold axis of rotation, that is called C2 axis. So here for the water molecule, we have to perform two-fold axis of rotation in order to get equivalent configuration. So that's why for water molecule, the axis of rotation exists is called C2 axis. The order of an axis can be seen as the number of times that the smallest rotation is capable of giving equivalent configuration, or the number of times it must be repeated to give an identical configuration. We have shown above that the case of molecule, a 180-degree rotation performed twice give an identical configuration. So in the water molecule, the axis of symmetry is C2 axis of symmetry, and the first step after 180-degree so rotation we will get equivalent configuration, so that is called C2-1, and after the second so rotation again we will get the identical condition, that is called C2-2. Now let us consider some other examples. So here, so we will consider the example of ammonia molecule. We know that the shape of the ammonia molecule is trigonal pyramidal or simple pyramidal. So this is pyramidal. The shape of the ammonia molecule is simply pyramidal or trigonal pyramidal. The structure is, the three-dimensional structure is like this. Here one lone pair of electron is there, right? So now in the ammonia molecule, so this is the three-dimensional image of the ammonia molecule. This one is the three-dimensional image of the ammonia molecule. The central atom, this is the nitrogen atom that is attached to three hydrogen atoms, H1, then the second one is H2, and the third one which is not visible to us, that is this one, the backside hydrogen atom, that is called H3. Now, if we rotate the molecule by 120-degree, you will observe that H2 will move to the position of H3. The So here we have taken the example of ammonia molecule. So you can see in the ammonia molecule, the structure of the ammonia molecule is trigonal, pyramidal or simply pyramidal. So here this is the structure of ammonia molecule. So in the ammonia molecule, the blue, so the central atom is nitrogen atom, and the three hydrogen atoms are mentioned as H1, H2 and H3. So the three hydrogen atoms are H, so this is the central nitrogen atom. So this is the nitrogen atom. This is first hydrogen atom H1. This is the second hydrogen atom H2. And the back side you can see this one, that is the third hydrogen atom H3. So that is the third hydrogen atom H3. Now if you rotate the molecule by 120 degree, so then what will happen? The H2 molecule, the position, the second hydrogen atom will go to the third one. So this one is H2, so that will go to this position, the third position, and the third hydrogen atom which was in the back side, that will move to the H1, this position, the first hydrogen atom position, and the first hydrogen atom will move to the H2 position. So the H1 will move to H2 position, H2 will move to H3 position, and H3 will move to H1 position. So that after the, so rotation by 120 degree, we will get identical structure. Hence, that is called, so 120 which is equals to 360 divided by 3. So that's why that is called a three-fold axis of rotation for ammonia molecules. So three-fold symmetry axis of rotation. Here you can see in case of ammonia, a rotation by 120 brings the molecule to an equivalent position. In case of ammonia, the rotation by 120 brings the molecule to an equivalent position. Therefore, we say that it has a C3 axis of rotation, that is 120 equals to 360 divided by 3. So that will get three-fold axis of rotation. Now the order of the axis is 3, and after 3 successive C3 rotation, the molecules come back to the identical position. So the successive C3 rotation, that is rotation through 120 degree, rotation through 240 degree, and rotation through 360 degree, are denoted by the symbols C31, C32 and C33 respectively. You may note here that the operation C31 and C32 leads to equivalent configuration, while the operation C33 gives the identical configuration. So this one, the first one, in the first step, the operation is C31, that is rotation by 120 degree. In the second step, the operation is C32, that is due to rotation by again 120 degree, that means a total of 240 degree. So that will give identical equivalent configuration. But if you will perform the same experiment once again, that is, so rotation by 120 degree, so that will give the identical configuration. Thus ammonia molecule is more symmetrical than water molecule, as it looks some, as it looks the same after the rotation by 120 degree or 240 degree or 360 degree. But in case of water, it looks like the same after the rotation with 180 degree and 360 degree. So water molecule has a two-fold axis of symmetry, but in case of ammonia molecule, it has a three-fold axis of symmetry. And similar type of, if you consider another example, that is boron trifluoride. So here this is the boron atom and these are the three fluorine atoms. So the shape of the molecule is trigonal planar and the bond angle is 120 degree. So if we rotate the molecule by 120 degree, we will get identical configuration, equivalent configuration, and after that if we perform another 120, that means a total of 2 to 240 degree, that will give rise to another equivalent configuration. And if we rotate the molecule still more 120 degree, that is a total of 360 degree, so rotation, you will get identical configuration. So that's why the boron trifluoride has a threefold axis of rotation, that is C3 axis of rotation. And similarly, in addition to that, the boron trifluoride molecule has three two-fold axis of rotations, also passes through the boron atom and one of the fluorine atoms are shown below. Suppose if we consider the axis, this one, this is C2 axis. And similarly, there will be three C2 axes are there. So that's why that is called a three two-fold axis of rotation. Now coming to, if the molecule has more than one CN axis of different order, then the axis of highest order is called principal axis. Again, if a molecule has more than one CN axis of different order, then the axis with highest order, that is called principal axis of the molecule, and defines the vertical direction of the molecule. Thus, C3 axis of the boron trifluoride molecule is the principal axis, although it has another three two-fold axis of symmetry. Now let us consider the rotation of the square planar structure of PCl4 minus. So this is the square planar structure. So if we perform the rotation of the PCl4 minus, you will observe that, so there is for this molecule, so one exists a four-fold axis of symmetry. So here two C4 operations in a row are equivalent to a C2 operation, and four successive C4 operations in a row gives back to the identical molecule. Now let us see what happens if we perform a C4 operation. C4 operation means, so here the n value is 4, and hence the angle of rotation should be 360 divided by n, that is equals to 360 divided by 4, which is equals to 90 degree. So we find the result of 90 degree rotation anti-clockwise direction is same as that of the successive 90 degree rotation in the clockwise direction, that is C43. So the anti-clockwise rotation is referred as an inverse rotation operation, and it is identified using a minus sign, that is C4 minus 1. So that means, so C4 minus 1 equals to C43. C4 minus 1 is exactly same as C43. In general, the inverse of CNM is CNN minus M. Now let us consider the methane molecule. So we know that the structure of the methane molecule is tetrahedral. So the methane molecule has three two-fold axes of rotation, apart from the four three-fold axes of rotation passing through the carbon atom and one of the hydrogen atom. So here you can see, so this is the structure of the methane molecule. So in the methane molecule, this one is one C2 axis, this is another C2 axis. So this is one C2 axis, this is another C2 axis, and this is another. That means that has three C2 axes. That means it has three two-fold axes of rotation. And similarly, if we consider C3 axis, if the axis will passes through like this, so we know that, so this is the structure of methane, tetrahedral structure of methane. This is the tetrahedral structure of methane, and if the axis passing through the carbon and one of the hydrogen atom, so this is the tetrahedral structure of methane. So if one imaginary axis passes through the carbon and hydrogen atom, then that is called C3 axis of rotation, and similarly there will be 4 C3 axis of rotation. So the 4 C3 axis of rotation what? You can see the 4 C3 axis of rotation. This one is first C3 axis of rotation. This is another C3 axis of rotation. This is another C3 axis of rotation, and this is the fourth C3 axis of rotation. So let us look for the axis of rotation in case of benzene. So if we consider benzene molecule, so in case of benzene molecule, there is one six-fold axis of rotation perpendicular to the plane of the ring, as shown a small green circle at the center of the molecule. So if this is the structure of the benzene molecule and one axis perpendicular to the center of the, if we imagine an axis passing through the center of the molecule perpendicular to the plane, then that is called six-fold axis of rotation, or that is called C6. So that is the rotation of the molecule by 60 degrees around this axis, then we will get an equivalent molecule. In addition to the principal axis of rotation, that is in addition to the to in addition to the principal axis of rotation in case of benzene. So in case of benzene, the principal axis of rotation is one six-fold axis of rotation or one C6 axis of rotation. Apart from that, another six numbers of two-fold axis of rotation perpendicular to the six-fold rotation axis as shown below. So the principal axis of rotation is six-fold axis of rotation, that is called C6 axis of rotation, and apart from the C6 axis of rotation, another six C2 axis are there. So this is one C2 axis, this is another C2 axis, this is number 3, this is number 4, this is number 5, this is number 6. C2 axis of rotation means you have to rotate the molecule through 180 degree. And the symmetry element for a molecule are in a space. These do not these do not move in the process of executing a symmetry operation. For example, in benzene, the atoms can be moved between any 6 possible arrangements using the principal axis. In all these arrangements, the C2 axis remain a symmetry element. So the six two axes meet the principal axis and they have one angular spacing of 60 degree. Since after a C6 rotation, the arrangement of the atoms around the C2 axis is shifted to one of its neighboring position, we say that all the C2 axes have an equivalent environment of atoms. In the other word, they are equivalent axes. You may note that there are two types of two-fold axis of rotation in case of benzene. One of these passes through the opposite corner of the hexagon, and you can see one of so there will be six number of C2 axis or six number of two-fold axis of symmetry, but the six number of two-fold axis of symmetry are categorized into two types. So the first one is blue color. So this one is blue color, three blue color C2 axis of symmetry. So the three blue color C2 axis of symmetry through the passes through two carbon atoms opposite to one another. So you can see the three blue colored C2 axis of symmetry. So the three blue colored C2 axis of symmetry passes through two carbon atoms each apart from the center of the molecule. And similarly, another type of C2 axis of symmetry that passes through without any atom, but that will divide the molecule into two equal half parts. So these are red color, number 1, number 2, number 3. So a total of, so the six C2 axis of symmetry meet the principal axis and have an angular spacing of 60 degree. Since After a C6 rotation, the arrangement of the atoms around any of the C2 axis is shifted to one of its neighboring position. We say that all the C2 axes have an equivalent environment of atoms. In other words, they are equivalent axes. You may note that there are two types of two-fold axis of rotation in case of benzene. One of these passes through the opposite corners of the hexagon, that means the opposite carbon atoms along the opposite carbon hydrogen bonds of the ring, whereas the second type of the C2 axis passes through the midpoint of the opposite and parallel side of the benzene hexagon and bisect the opposite carbon-carbon bonds. And similarly, if we consider other molecules like linear molecules such as H2, HCl, carbon dioxide, COH, that is carbon oxygen sulfide. So they have C infinite axis along their molecular. So you will consider the carbon dioxide molecule. This is the carbon atom, this is one oxygen atom, and this is another oxygen atom. So this is carbon dioxide molecule having linear shape. So this is C infinite axis of rotation, because here the value of n, you can take any angle of, so if you rotate the molecule through any angle, identical configuration will obtain. So that's why the angle of rotation it tends to 0. That's why 360 divided by 0, so that will give to infinite. So that is called C infinite axis along their molecular axis, since the rotation through any small angle around the molecular axis gives rise to an equivalent configuration. In the other word, the angle of rotation for obtaining equivalent configuration is infinitesimally small, that is tends to 0 for linear molecule. Therefore, the order of axis n equals to infinite. For example, in case of carbon dioxide, C infinite axis can be observed. So this is about axis of rotation. And after that we will discuss the plane of symmetry. A plane of symmetry is an imaginary plane that divides the molecule into two equal halves, such that one half of the molecule is the mirror image of the other half of the molecule lying on other side of the plane. It is also known as mirror plane and is represented by symbol sigma. So the symmetry operation associated with the plane of the symmetry, that is called reflection. So the plane of symmetry is also called as reflection. So when one reflection operation is carried out over the plane of the symmetry, we get a configuration that is equivalent to the original configuration. All planar molecules have their molecular plane as one of their symmetry elements, that is a mirror plane. Because atoms lying in this plane are not affected by the reflection. In general, there are three types of mirror planes perpendicular to their relationship with the principal axis. So here we will discuss three types of mirror planes are there. So, or three types of plane of symmetry are there. So we will discuss what are the three different types of plane of symmetry exist for the molecules. So the first plane of symmetry, that is called a mirror plane, that contains the principal axis. If you will imagine one mirror plane passing through the principal axis means the highest pole axis of rotation is called principal axis. If you will remember the previous example, that is in case of benzene, one six-pole axis of rotation was there. Apart from that six-pole axis of rotation, six two-pole axis of rotation also exist. That means one C6 axis of rotation and six numbers of C2 axis of rotation. So the principal axis of rotation is C6 axis of rotation is called principal axis of rotation. Now if the mirror plane contains the principal axis of rotation, or if the mirror plane contains the principal axis, it is called vertical plane and it is denoted as sigma v. On the other hand, if the mirror plane is perpendicular to the principal axis, it is called horizontal plane and it is denoted as sigma h. A vertical plane of symmetry that bisects the angle between the two C2 axes in the molecule, that is called a dihedral plane, that is represented as sigma d. Now let us take some examples and learn about the different planes of symmetry, that is sigma v, sigma h and sigma d. So first we will discuss about the sigma v. Now a water molecule has two vertical planes of symmetry. So here, so the first one is, this is the, so the first one of these is the plane of the molecule, and the other one is the plane perpendicular to the molecule. So this is the plane of the molecule. So the plane of the molecule is also one sigma v symmetry. And similarly, the another one is the plane passing perpendicular to it. So this one, so that is the plane so that is perpendicular to the plane of the molecule. So these are distinguished by the plane perpendicular to the molecule as sigma v, whereas the plane of the molecule itself as sigma v dash. So for water molecule, so there are two plane perpendicular. So for water molecule, two vertical planes of symmetries are there. For water molecule, two vertical planes of symmetries are there. The first one is itself, that is the plane of the molecule. So this is the plane of the molecule, and the second plane, that is perpendicular to the plane of the molecule. So the plane that is perpendicular to the plane of the molecule, that is designated as sigma v, and the plane of the molecule itself is called sigma v dash. Here the symmetry element is the mirror plane itself, and all the points of the plane remain unchanged by the reflection operation. Now if you consider the ammonia molecule, on the other hand, it has three vertical planes of symmetry. So each one of these passes through the nitrogen atom and one of the hydrogen atoms and contain the threefold axis of symmetry as shown as in the figure. So for ammonia molecule, so the ammonia molecule contains three vertical plane of symmetry. So this is the first vertical plane of symmetry, this is second vertical plane of symmetry, and this is the third vertical plane of symmetry. So the two successive reflection operation brings the molecule back to the original configuration as shown below. So this is one success. So it will perform reflection along this plane. It will perform reflection along this plane. Then H1 will move to this H2 position, and H2 will, so that means there will be interchange in the position of the two hydrogen atoms for water molecule, and if we will perform same operation again, we will get the identical molecule. Now let us consider the example of benzene. So in benzene, the plane contains all the 6 carbon atoms and the 6 hydrogen atoms, that is the molecular plane is the horizontal plane, it is perpendicular to the C6, it is so this one is the molecular plane. So the molecular plane is perpendicular to the principal axis. Here in case of benzene, the principal axis is C6 axis is the principal axis. So in case of benzene, the molecular plane is perpendicular to the C6 axis. So that's why the molecular plane is called sigma h. In addition, benzene has 3 vertical planes. That means in addition to this, benzene has 3 sigma v planes of symmetry. These planes passes through the 2 opposite carbon hydrogen bond and cut the molecule into 3 halves as shown below. So this is the first vertical plane of symmetry. So this is the first vertical plane of, you can see this is the first vertical plane of symmetry, and this is the second vertical plane of symmetry. Apart from this horizontal plane of symmetry, The benzene molecule contains three vertical plane of symmetry. So a vertical mirror plane that bisects the angle between the two C2 axes is called dihedral mirror plane. So these are three such. So there are three such dihedral mirror planes in the benzene molecule. So this is sigma D1, sigma D2, and sigma D3. So this is about dihedral plane, sigma D, and sigma H, and sigma B. Now coming to the improper axis of symmetry, that is called Sn. So the n-fold proper rotation is a composite operation, and so how difficult and somewhat difficult the symmetry operation to identify the molecule. It consists a proper n-fold rotation about an imaginary axis followed by the reflection through a plane perpendicular to it. So the axis about which this operation is performed is called axis of improper rotation, and it is denoted by the symbol Sn, where n, as before indicated, that is the order of axis. Such an axis is also called as rotary reflection axis or alternate axis of symmetry. So the axis of this axis is called improper because the object does not need superimpose to the original object after the rotation. So it is after the second step. That means so the improper axis of symmetry is the combination of two different steps. The first step is reflection through a mirror plane perpendicular to the improper axis, and again, so that is the reflection through the mirror plane perpendicular to the improper axis, so that we get the original object back. In fact, the operation is complete only after the reflection step. So the symmetry operation around this axis, that is the rotation followed by the reflection, is called improper rotation. So that means improper rotation contains two different steps, so that we will get identical configuration. And the two different steps are rotation followed by reflection. So if rotation followed by reflection give exactly identical equivalent configuration, then that is called improper rotation of symmetry, and that is designated as symbol Sn. So here the n signifies the number of pole. So the number of angle of so the angle of rotation can be known from 360 divided by n. So if the value of n will be 3, so the angle of rotation in the first step, that is 360 divided by 3, which is equal to 120. It is important to note here that for all the rotation reflection operations to occur, neither the existence of a proper rotational axis nor a horizontal mirror plane is essential, though they may exist. For example, let us consider ethene in its staggered configuration. So we see, you can see ethane in its staggered configuration. So this is the structure of ethane. We know that ethane is CH3, single bond CH3. So here this is the staggered configuration of ethane. So the first one, that is the staggered configuration of ethane. So in the staggered configuration you see, so this is one hydrogen, this is second hydrogen, it is third hydrogen. So one CH3 group is here, and the another CH3 group is, so this one another CH3 group. So in the staggered configuration, if we rotate the molecule through 60 degree, the configuration will become, if we rotate the molecule through 60 degree, the configuration will become like this. So this hydrogen atom will move to this position by 60 degree, and the bond angle for this hydrogen, carbon and hydrogen is 120 degree. That means the hydrogen atom moved to the middle position. So this is the rotation by 60 degree, that is called C6. And after that, if you imagine one reflection of this plane, you will get identical configuration as the initial one. So that means here C6 sigma H. Rotation by 60 degree and after that reflection. So that's why that is called A6 axis of symmetry, or that is designated as S6 improper axis operation. S6 improper axis operation. On the other hand, we may have the classes like the examples of MX4, which has C4 axis as well as sigma H plane. So it will have S4 axis of operation, S4 axis of rotation. And similarly, another example of a molecule with improper axis is the methane that has S4 improper axis. It involves the rotation by 90 degree around the carbon hydrogen, around the hydrogen carbon hydrogen bond, followed by reflection. So you can see reflection, rotation of this molecule by 90 degree, and it will so that will in the first step, rotation of the molecule by 90 degree will give to this type of structure, and after it will do the reflection operation, that is sigma H, so that will get the identical structure. So that type of operation is called S4 improper axis. Now coming to center of symmetry. So the next operation that is called center of symmetry, that is inversion operation will be there. So here inversion operation will be there. Now, if we suppose consider the SF6 molecule which has the tetrahedral structure, SF6 molecule having the SF6 molecule having the octahedral structure. If we consider the SF6 molecule having octahedral sulfur hexafluoride, SF6 molecule as shown in the figure. Here, the molecule has center of symmetry. So, center of symmetry means if we invert the molecule, then F1, this is the central sulfur atom, and these are the 6 fluorine atoms, F1, F2, F3, F4, and F6. So, if we invert the molecule, or if we perform the invert operation, then F1 will move to F2 position, F2 will move to F1 position. Similarly, F4 will move to F6 position, and F6 will move to F4 position. Similarly, F3 will move to F5 position, and F5 will move to F3 position. So, on executing the inversion operation, each of the fluorine atom is moved through the center of the symmetry to the other side. As a consequence, the fluorine atoms swap their positions, like 1, 2 will swap their position, 3, 5 will swap their position, 4, 6 will swap their position, whereas the position of the sulfur atom does not change, as will get an equivalent configuration. If we perform the inversion operation twice, we will get back the identical configuration of the molecule. It is important to note that the only one inversion operation is associated with a given center of symmetry. Now coming to identity E. The operation identity E is a trivial operation and consists doing nothing to a molecule. That means no operation is performed. So the symmetry element here is the entire molecule. Therefore, all molecules, whatever the structure, all molecules possess the identity element. It is an equivalent to so the operation identity element is equivalent to rotation of the molecules by 360 degree, and irrespective the shape structure of the molecule and any types of atoms may present in the molecule. So if you rotate the molecule by 360 degree, exactly equivalent configuration will find. That's why that is called identity molecule. That means in case of identity molecules, the operation is doing nothing. That is called identity. It will do nothing. That is called identity molecule. Therefore, the choice of axis is also. So this is identity. So here this is the suppose this is the carbon atom. This is first one is hydrogen, then chlorine, then fluorine, then bromine. That means completely different atoms are attached to, completely different four atoms are attached to the carbon atom to form the tetrahedral chlorofluorobromomethane. And if you will do the identity operation, that means if you rotate the molecule by 360 degree, exactly same will appear. That means doing nothing. So this type of symmetry element is called identity. Then you have noticed that all the symmetry operation discussed above on the successive operation will get an original molecule back. That is, if nothing has been done to the molecule, in other words, generation of identical configuration of successive operation is equivalent to identity operation. And you may verify the following: C22 is equivalent to identity operation, C33 is equivalent to identity operation, C44 is equivalent to identity operation, and so on. Similarly, sigma V2 is equivalent to identity operation, sigma H2 equivalent to identity operation, sigma D2 equivalent to identity operation, and inversion I2 is also equivalent to identity operation. So for improper rotation, it can be shown that two successive S4 operations are equivalent to C2 operations. So S42 is equivalent to C2, and executing two more successive S4 operation, that is a total 4 S4 operation will give to identity operation. So S44 equivalent to E. So here you can see define the question here you can see define a symmetry operation, and the second one taking the example of pH3 molecule exactly equivalent to the NH3 molecule, ammonia molecule, whose structure is given below, so that C3 minus 1 C3 inverse is same as C32. So you have to show in case of pH3 molecule. And the next one, allene, also known as propadiene, that contains two adjacent carbon atoms. So this is the carbon atom, this is another double bonded carbon atom, this is another double bonded carbon atom after two hydrogen atoms. So the two hydrogen atoms are like this. So in case of allene, so that it has S4 improper axis of symmetry, that is its structure is given here. And then what is the order of the principal axis of rotation in case of benzene molecule? And identify the symmetry element of the following symmetric graphic. So here you have to find out which type of symmetry elements are there for this graphic. And this is about the symmetry elements. And after that, the next part is point groups. So here we'll discuss about the point group. Point groups. So the point groups are a system of classification used to describe the symmetry of the molecules. Again, I'm sharing that one. So the point groups are a system of classification used to describe the symmetry of molecules. A point group consists of all symmetry operations such that identity operation, rotation operation, reflection operation, inversion operation, identity operation, etc. So that leave a molecule unchanged or invariant, that is called a point group. A knowledge of the point group for a molecule is important to understand the electronic and vibrational states of the molecule. To learn about the classification of the molecules to point groups, we need to first understand what are the groups, that is, and what are their corresponding characteristics. So here we will discuss the groups and their characteristics. So as discussed above, a given molecule in its equilibrium configuration can show a number of symmetry operations that we have discussed in the previous part. The number of symmetry operations will show that these symmetry operation form a mathematical group with characteristics property. So the element of a group are related to another through a combination process where that may involve multiplication or addition. So the groups of the symmetry operation for a molecule are referred as point groups because one of the points in which one of the point in the molecule is left unchanged by any operation. So the point groups means so the molecule should left unchanged by any operation, that is the point of the molecule remain invariant. It is important to know that there are that this point is not necessarily occupied by the nucleus. So there are two systems for representing the symmetry operation. So the two systems, so representing the different symmetry operation. The first one is confile symmetry, so that is the confile symmetry, and the second one is Hermann-Naugin symmetry. So that is called HM symmetry, and particularly this HM symmetry used in solid state, that is for crystallography, and in confile symmetry used for the gaseous molecules. Now, let us start outline the requirement for formation of mathematical groups that must be satisfied by the collection of operation from a group. And these are the first one is identity operation E must be a member of the group. So, in order to construct a mathematical table, so the identity operation must be a member of the group. We have discussed about the identity operation in the previous part, and it is stated that it is present in all molecules, whatever may be the structure of the molecules or the molecule contains in which atom, any atoms, but definitely identity operation will be there. It commute with all the other members of the group, that is AE, that is AE equals to that is EA equals to AE equals to A, and similarly EB equals to BE equals to B, where AB are the members of the group. Now coming to the next one, the operation corresponding to the successive operation of the two members of the group must be member of the group. It will simply means that the product of two symmetry operations of the group gives another operation of the group. That is, if A and B are two operations of the group, then the combination AB is also a member of the group. Then the third one, an element combined with itself to form one of the element of the other group. It simply means that the square of an operation is also a member of the group. Every element of a group obey associative law. The fourth part is every element of the group obey associative law. That means if A, B, C are the three operations what I've discussed in the earlier part, if A, B, C, if A, B, and C are the three operations, then that should follow associative law. That means A, B, C. That is the associative law means bracket A, B, C. That will give rise to A bracket B, C. So here this means A and B will be operated first, and after that C. And in the similar way, A will operated first, and after that B and C. So the element, the fifth point is that the element need not be commutative under multiplication. So the commutative means AB equals to BA. So that is the combination of AB need not always be equals to BA. That is the order of combination is important. In the group in which AB equals to BA are said to be commutative or abelian groups. Now coming to the sixth point, each operation must have a unique inverse that returns the object to the original position, that is the element, and the inverse combined to give identity element. So here that means the element is A, so that will operated over inverse. So A is one operation, and if that will be multiplied with its inverse, so that means A inverse, that is equals to A inverse A. which is which should be give the identity operation. So you will recall from the above, the water molecule has four symmetry elements. So if you consider the water molecule, it has four symmetry elements. So the first one is it will have C2 axis of symmetry. It will have identity. It will have one xz plane. So that is sigma v, and another one is dihedral sigma yz. So the four. So the first one is identity, two-fold axis of symmetry C2, and two vertical planes, that is sigma v and sigma v dash. So now let us see whether these symmetry element must be requirement of the group. First one is presence of an identity element, yes. The second one is successive execution of the two symmetry operation give another member of the group, that is yes. For example, C2 sigma V, that will give rise to V, sigma V sigma V dash, that will give rise to C2. So C2 is present. Then sigma v dash, sigma v, that will give to C2, that is also present. Then sigma v e equals to sigma v, that is also present. And the third condition, a symmetry element combined with itself to give another element, that is also yes. So that means C2 combined with itself, C2 dot C2, that should be E, sigma V dot sigma V, that is E, sigma V dash, that is E. And the fourth point, associative law holds for the different element, that is S. For example, sigma 2 sigma V, then sigma V dash, which is equal to E, or sigma 2, then sigma V dash, that is also equal to E. Then every element has an inverse. For example, uh, C2 dot C2 inverse dot C2 equals to E, and so on. So we find the symmetry element of the water molecule meet all the requirement of the group. So the above information can be presented in the form of a table, that is called group multiplication table, and it's given below. So these are the four symmetry elements present in water molecule. First one is E, the second one is C2, so that is the Z axis. The third one is sigma v, that is xz plane, and the fourth one is sigma v dash, that is the yz plane. And similarly, so these are the four. So here, if E multiplied with E dot E, that will give to E. Then in the similar manner, you will fill the table. Then suppose C2 dot C2, that is gives rise to E. For example, sigma V dash sigma B, that will give rise to E, or sigma V dash multiplied with sigma V dash sigma V dash multiplied with sigma B, that will give rise to C2. So in the similar manner, you have to complete the group multiplication table. So here we will stop that, and after that, if possible, we will discuss the remaining parts.
କ୍ଲାସ୍ ସରିଗଲା।